Opportunity had come to rest in a small crater near the equator, at a spot called Meridiani Planum. Here in plain view, on a nearby crater wall, its camera revealed exposed bedrock, the first ever seen on Mars. Not far away, the rover found layered rocks on the face of a cliff. On Earth, they typically form as sedimentary layers at the bottom of oceans. And at every turn, Opportunity rolled across tiny, smooth, round pellets. They became known as blueberries because they appeared purplish-brown against Mars' rust-colored surface. Initially thought to be volcanic in origin, they turned out to be iron-rich spherules of the type that form within cavities in the mud at the bottom of an ocean. Drilling into rocks, the rover inserted a spectrometer to read the mineral content. The readings showed significant amounts of sulfate salt, a tracer for standing water. That wasn't all. Spirit's broken wheel dragging behind it exposed soils saturated in salt. Clearly, there was once water on Mars' surface. But how long ago? And if there's anything left, where would you find it? One possible answer: the North Pole. From orbit, this region seemed to be covered in frozen CO2, what we call dry ice. But was there water ice below the surface? Enter Phoenix, a lander that touched down near the North Pole in early 2008. Radar readings from orbit, taken by the Mars Express mission, hinted at the presence of ice just below the surface. The Phoenix lander's descent thrusters blew away the top layer of soil, allowing its camera to snap pictures of what looked like ice. Scientists instructed the robot to conduct a simple experiment. Reach out and dig a trench. Then watch what happens. As expected, clumps of white stuff appeared. A couple of days later, it was gone, vaporized. That means it can't be salt or frozen CO2, which is stable in the cold, dry temperatures of the Martian pole. So it had to be water, the first ever directly seen on Mars. There are indications that the North Pole was actually warm enough in the recent past for water ice to become liquid. The Mars Reconnaissance Orbiter, or MRO, used radar pulses to peer beneath the surface of the ice cap. These data revealed that the ice, just over a mile thick, formed in a succession of layers as the climate alternated between warm and cold. Our planet avoids mood swings like this, in part because its spin is stabilized by a massive moon. Mars' spin is not, so it can really wobble, with the pole tilting toward the sun for long periods. New observations by the MRO spacecraft show that these wobbles can lead to dramatic releases of CO2 and warming periods due to an increase in the greenhouse effect. The ice now detected below Mars' surface is a remnant of a much earlier time. The thinking is that not long after its birth, the planet's molten interior would have spewed out enough gas to form an atmosphere. Carbon dioxide and water vapor began to trap heat from sunlight. Temperatures rose high enough to allow liquid water to flow on the surface, creating myriad rivers, ponds, lakes, and oceans. Evidence of this thicker atmosphere landed literally in Opportunity's backyard. the rover spied a strange bluish rock, a nickel-iron meteorite named Block Island. Streaking through a thin atmosphere, this massive chunk of metal should have been obliterated on contact. Instead, its fall was likely slowed and its impact softened by a much thicker atmosphere. What then caused the atmosphere and the water to disappear, and the planet to grow cold and dry? The answer comes from data recorded by the Mars Global Surveyor just after it went into orbit in 1997. Its instruments detected the presence of a weak magnetic field emanating from the planet, a reading that scientists eagerly compared to that of Earth. Our planet's magnetic field is generated by molten rock deep in its core that rises and falls into a vast region below the outer crust called the mantle. The rising and sinking motion within, combined with the spinning motion of the planet, generates a strong magnetic field. You can trace this field back to Earth's early years, when large amounts of heavy elements such as iron sank into its core. Radioactive decay began to generate heat, and the planet's mass is large enough to hold it in. Earth's magnetic field extends far enough out into space to deflect the wind of high-energy solar particles. Without a similar electromagnetic deflector shield on Mars, solar radiation lashed the planet, gradually stripping it of its atmosphere. What water Mars had would have vaporized into space, or frozen underground. However, there is evidence that at one time, Mars did have a robust magnetic field. Rocks in some of the older craters bear a strong imprint of this field, while newer craters indicate a much weaker field. What happened to it? The answer lies deep in Mars' past, in events so powerful they are still written on the landscape. This is a simple elevation map of Mars' surface from data gathered by the Mars Odyssey spacecraft. The South Pole, colored in red and orange, is piled high with ice. Moving off these southern highlands, we make our way north. The landscape is pocked with craters. The largest and oldest ones have faded, their edges softened by wind-blown dust. Moving up along the equator, we pass into a region called Tharsis, based on a biblical name for the western edge of the known world. On the edge of this vast high-altitude plateau is a series of enormous volcanoes. Ascraeus Mons, 18 kilometers high. Arsia Mons, 16 kilometers. Pavonis Mons, 14 kilometers. Just beyond is the largest volcano in our solar system, Olympus Mons, 25 kilometers in elevation.